Hello and welcome to Circuit Crest TV. I'm your host Brian Jenkins and welcome to Tutorial 11, an introduction to variables. Now, those that have studied algebra will be familiar with equations such as this one right here, where x is an unknown variable one needs to solve for. For this equation, I'll use the term unknown loosely, as many of us can probably solve it by inspection. However, algebraic equations aren't always so simple. In this equation above, x can take on different values if we change the right side of the equation. In other words, the value of x varies depending on what we set the right side equal to, hence the term variable. Enough algebra. The concept of variables in programming is very similar. The internet tells me that in programming, a variable is a symbolic name given to an unknown quantity that permits the name to be used independent of the information it represents. That's sort of abstract. A better abstraction, at least for now, is to think of a variable as a container that holds something. When you were in middle school or high school, your algebra book might have been stashed in your locker when not in use. And if you're anything like me, your algebra book probably spent most of its time in its locker, barely seeing the light of day. Now, imagine a bank of lockers. Each locker is a container that can hold something. Let's say I want to write a program that checks the temperature every so often and logs the highest temperature in a given day. For this, I'll need two lockers. I'll need one to store the current temperature, and I'll need another to store the highest temperature. When we first start, the two will be equal. For example, say I start logging temperatures at midnight because that's technically the start of a new day. It's 58 degrees Fahrenheit outside, so not only is that the current temperature, it's also the maximum so far, as we've only taken one sample. But as the day progresses, both will update and change, and eventually the temperature will reach a maximum before falling again. So at noon, the temperature is 88. We'll take the number 88 and put it in both lockers. Then at 2 p.m., the temperature drops to 85. Now we'll put 85 in the current temperature locker, but we'll keep 88 in the high temperature locker, as 88 is the highest temperature so far today. The current temperature will continue to vary throughout the day. The high temperature will vary until we reach the maximum for that day. Now, here's the point. Think of variables as containers that hold something. Now, if you're new to Arduino, your next question might be something like, what else can I put in a variable? We know that different containers are good for storing different things. We also know that it's very helpful to have the right container for the thing we want to store. Let's use a typical grocery store as an example. Eggs are stored in an egg carton, which is appropriate because it protects them and makes them easy to access. You'll often find milk in a plastic gallon jug. Sometimes coffee is vacuum packed in little bricks. We know it wouldn't make much sense to put a gallon of milk in a plastic bag rather than a jug, nor would it make sense to try to vacuum pack raw eggs, and we wouldn't pack coffee in an egg carton. So it is with variables. Each type of variable is good for storing certain things. This is referred to as the variable's data type. Going back to our temperature locker example, we may want to use an integer data type for this if we're only interested in whole numbers. To do this, we need to declare two integer variables. We have the current temp and the high temp. In general, when we're declaring a variable, the form is data type first, then the variable name, and then you can set it equal to something. Notice though, that we didn't set our two variables equal to something, as this wouldn't make sense for our purpose. The temperature is what it is, and the variables will take on that value without us explicitly setting them equal. Setting a variable equal to something is referred to as initializing the variable, and it's optional. Sometimes you know ahead of time what the initial value of your variable will be. Sometimes you don't. In Arduino, we initialize variables with a single equal sign, which is called the assignment operator. Note that the assignment operator is not the same thing as the equal sign, which in Arduino and C is two equal signs next to each other. So here's the second point. Variables consist of a data type and a name, and initializing a variable is optional. In our temperature example, our variables were put in lockers. In a computer or microcontroller, variables are put into memory, usually some sort of register or the stack. Now, this is an introduction, so I won't go into too much technical detail about registers and stacks at this point. And there's another important point to note before we move on and talk about specific types of variables and what they're good for. There are certain words or names for naming variables that are off limits. For example, when programming in the Arduino IDE, we can't name a variable something like high or low. These are keywords the IDE reserves. Also, you cannot have any spaces in the name of a variable or special characters in the name of a variable, but underscores are allowed. And while you can use numbers in the name of a variable, you can't start the name of a variable with a number. Finally, the maximum size of these data types depends on whether you're using a 16-bit, 32-bit, or 64-bit processor. For example, an integer in a 16-bit system is 2 bytes. In a 32-bit system, an integer can be as large as 4 bytes. Since the Arduino Uno uses a 16-bit microcontroller, we're going to assume a 16-bit system. Just know that if you delve into a 32-bit system, like the Arduino do, or a 64-bit processor, the number of bytes a certain data type can hold will probably be larger. Now that we've had enough theory about variables and what exactly a variable is, let's dive into the Arduino IDE here and talk about some of the data types. We've already touched on integers, and out of all the data types, you'll probably use integers the most. As you may know, an integer is a whole number, which can be either positive or negative. The value of an integer can range from negative 32,768 to positive 32,767. Integers take up 2 bytes of data, regardless of the size of the number that you use. So if you declare an integer 0, it's still going to take up 2 bytes. Declaring an integer is really simple. We could just type something like int myInteger equals 800, or whatever you want it to be. However, you got to be careful to make sure an integer always stays within the range it's supposed to be, or really weird things can happen. For example, if we add 1 to 32,767, we won't get 32,768. Instead, it rolls over to negative 32,768. And this is because 32,768 positive is too big to store as an integer. And most data types will roll over once you exceed their maximum value, which will cause logical errors in your program that could be tough to find. So one of the main points here is that when you create any kind of variable, you need to have some idea of what type of value it will hold and how big or small that value will get. So what do you do if you need to work with a number like 62,543? That's where the unsigned integer comes in. An unsigned integer can only be positive, but its range is from 0 to 65,535, which effectively doubles the range if you know you're only going to be working with positive numbers. So if you live on a tropical island and you're logging the temperature, you know that you're never going to see anything drop below 0. So in that case, you could use the unsigned integer. And this example here shows how to declare an unsigned integer. Note that unsigned integers also will roll over, just like we talked about, to 0 if your program inadvertently adds 1 to 65,535. So be careful. Still need an even bigger number? No problem. Just use a long, which has a range of negative 2,147,483,648 to positive 2,147,483,647. And the example here illustrates how to declare a long. Now, longs take 4 bytes of data, regardless of size. Just like the other data types, a long will roll over if the value is exceeded on either end. And you can also have an unsigned long with a range from 0 to 4,294,967,295, like the example here. If that's not big enough for you, just use a long integer. To declare it, type something like long int equals something really huge. Its range is huge, and I'm not even going to bother trying to speak this number. But as you can see, you'll have plenty of space. And you could also use the unsigned prefix or qualifier with the long. But what if we need to store a number that's not a whole number like pi? If I try to put a number like pi into a variable with data type integer, I'm going to have problems. So if I declare an int like int pi equals 3.14, it's not going to work. That's where the float is used. The float data type has a huge range, but there's a catch which we'll talk about in 1 second. To declare a float, just type float, name your variable, and initialize it if you want. Another way to declare a float is to use the exponential notation. So if I put another float equals 3.14 E3, that's the same thing as saying 3.14 times 10 to the third, which is 3,140. A floating point number corresponds to what mathematicians call a real number, which includes numbers between the integers, like 1.1, 1.11, 1.2, etc. Floating point representation involves breaking up a number into a fractional part and an exponent part and storing the parts separately. And they occupy 4 bytes of space. However, we hinted earlier that the bigger the float is, the less precise it is. Now, depending on what you're doing, this may or may not be important. And what do we mean by precise? Well, because there's an infinite number of real numbers in any range, for example, between 1 and 2, computer floating point numbers can't represent all the values in that range. So we could probably get away with storing and retrieving a number like 1.1234 accurately. But if we try to store the number 1.2345678901234567889, we may run into trouble where the computer will drop some of the digits at the end or round the number to some nearest value. Next, we have the char. Char stands for character and takes 1 byte of storage. Normally, you'd use a char to hold a character such as a letter or a symbol. They range from -128 to +127. There are 2 ways to declare a char shown below. We can declare a char as a letter, like here, and if we declare a char as a letter, we need to enclose that letter or character in single quotes. Or we can declare it as a number, where we don't need the single quotes. Note that when you declare a char as a number, what's actually being stored is a letter or character whose ASCII value corresponds to that number. So in the second declaration here, the number 98 corresponds to a lowercase b in ASCII. And you can also use the signed and unsigned qualifiers with the char too. Here's a fun fact. ASCII stands for American Standard Code for Information Interchange. Next, we have the byte. The Arduino IDE uses the byte data type. This isn't usually found in regular C, but bytes take up, you guessed it, 1 byte of space, and they have a range of 0 to 255. These can come in handy if you're really pressed for program space, and you know your value won't go out of this range. And this example shows you how to declare a byte. Finally, there's the Boolean data type. Boolean values take up 1 bit, not byte, but 1 bit of space, and can either be true or false. That's it. If you put a non-zero value into a Boolean variable, it'll be considered true. So for example, Boolean my Boolean equals 37 evaluates to true. False can be represented by a 0, the word low, or the word false. So if we do a declaration like my Boolean equals 0, low, or false, all 3 of those above statements mean the same thing and are considered false. Similarly, the true state can be represented by the word true or the word high, in addition to any non-zero number. This data type would come in handy if a variable only needs to represent 2 states. I know all the stuff we've talked about so far is a heck of a lot to remember. So I went ahead and included this nifty little chart which summarizes the data types we just went over. Go ahead and do a screenshot or bookmark this video so you have this chart on hand. And that wraps up our tutorial on variables. In the next tutorial, we'll go into control structures. Until then, go forth and create. If you're interested in Arduino and microcontrollers, you'll love how to get started with Arduino in 1 day or less. Get instant access now by clicking the link below in the description.